Thank you. Can you hear me all right? Thanks. I realized I didn't put my name on this. So I'm Chloe Mackallah. I'm from CSIRO. I've been working in ACCESS for a little while, and I'm working now in ACS, which is the Australian Climate Service. I'm going to be, as a surprise to people who know me, I'll be talking about data, which hopefully isn't too boring. So we're talking about standardized data structures and sort of their importance for facilitating science. In general, I'll also be talking about our ACCESS GCM work for CMIT 6. I'll introduce the sort of the topic of a DRS, for those who don't know, which is a data reference syntax. And then I'll be talking about my work in the Australian Climate Service, some of our workflows, and some DRS kind of work that we're working on developing. I'm going to start with a really simple analogy of why data is important. In this kind of very, very simple framework, we've got science, which is a truck driving down a road, unstructured data, so ad hoc data, raw data that comes out of a model. This is unstructured data. It tends to encumber analysis, prevents intercomparison between models, and generally kind of tends to inhibit science because what I found is that a lot of scientists spend a lot of time battling data that isn't structured very well. Not really what I think is the best use of scientific time. And so structured data is much better for facilitating science. Streamlines analysis, you can use much better tools, enables intercomparison between models, as we've seen in CMIP, and generally sort of facilitates science and allows for a lot more of scientific time to be spent doing the analysis and not battling unstructured data that isn't very robust, doesn't have great metadata, and sort of that ad hoc system. So when I say structured data, I'm really talking about data in what we call a DRS. But first, I'm going to talk about our ACCESS workflows. These are the workflows that we applied to the CMIT 6 production runs, which were the ACCESS EM2 and ACCESS ESM that we submitted to CMIT 6. We had forcing data, obviously, that fed into the ACCESS simulations. Obviously, out of that, we had the raw data. This is data that is relatively chunked into months or years. When it comes out of the model, we're looking at PP files that are UM-based kind of files. Ultimately, these will get deleted as we sort of follow this processing along. We've developed a tool called the ACCESS Archiver. I know some people in Clex are starting to use it. This is really a pre-processor. It's really just a tool for taking the raw model output, and it's not doing a whole lot of processing. It's really just doing some compression, converting UM files to NetCDF, adding some simple metadata, basically just putting it into a form where you're not losing anything, you're not losing any information that's in the original raw model output, but this isn't fair data, this isn't publishable data, this is really just archival data that contains everything that was in the raw model output, just with some better structures and better compression. Ultimately, this will be archived onto tape systems and things like that for if details are needed, especially when it comes to, say, the land surface scheme, where you've got many tiles that ultimately will be compressed when it comes to the next step, which is the post-processing. This is the work that I was mainly doing for a couple of years when I joined CSIRO. We developed a tool called the APP, which is the ACCESS Post-Processor. It was developed originally for CMIT 5, which was the APP version 1. We've now got the APP 4, which was developed for CMIT 6. This will post-process the archive data. The ACCESS Archiver specifically was designed to feed directly into the APP. This will create structured data that we then submitted to CMIT 6. So the APP4 is what I used to generate all of the data that we submitted to CMIT 6, so roughly 600 terabytes. That can then be published. We've made the tool, the APP4, to be somewhat generalized so that it can be used for non-CMIT 6 experiments. So that you can put in whatever kind of metadata you want, experiment names, MIP details, those kind of details. However, the data that it's generating is CMIT 6-like data. So it's really useful for researchers who are running CMIP6-like simulations, especially with CM2 or ESM, doing sort of extra experiments like Ariane showed yesterday. And you can use these tools to then create data that looks like CMIP6 data that you can compare directly to the CMIP6 data, create all the variables, and it just facilitates that intercomparison between comparing to control simulations to the sort of the more niche kind of simulations. I'm going to talk about the CMIP6 DRS. So that the AP4 creates DRS data. This can then be fed into more standardized analysis tools. ESM-Vel tool is one type tool, but there's many. And so putting data into this DRS type structure is then very important for all of these analysis. What is a DRS? Very simply, a DRS is a list of a controlled vocabulary. So we've really just got like a list of defined terms. We've got directory structure that is well defined and uses the controlled vocabulary. We've got a file naming convention. We've got metadata requirements, attributes, definitions, that kind of thing, and data format requirements, which are, things like the number of levels, pressure levels. We've got 19 pressure levels in monthly data and 8 pressure levels in daily data, those kind of details, and obviously NetFTDF4 as well. The main points are that it's a controlled vocabulary, there's a fixed directory structure, and a file naming convention. What it looks like in reality, this is what you would find if you searched for the CMIP6 DRS. It's not awfully pretty, but it kind of highlights what the main parts of what the DRS is. Directory structure based on these various terms. I'm sure people kind of are somewhat familiar with this, where you've got CMIP6/CMIP/ CSIRO / ACCESS-CSM, blah, blah, blah. And then we've got file name convention, which obviously uses the same vocabulary. This is not awfully useful for really describing what it looks like in practice. So I've got this schematic that I drew up, which really kind of shows the various items in each of the directory structure components. So we've got different MIPS. We've got obviously we've got the different institutions and their models, the experiment IDs that all got branched off, ensemble members, tables, variables, grid labels, versions, file names. And so it really just creates this very expansive tree of data in a controlled vocabulary sense. So it's very useful for feeding into, obviously, these standardized tools. It enables more sort of controlled ways of accessing this data. I haven't put a slide in here, and I think I will add one. There's a tool called Intake ESM, which is a sort of a data cataloging tool that you can then input all of this sort of file structure into this, and then you can interact with it in a much more interoperable way. This is FAIR data. This meets all of the FAIR standards. In fact, this is the worldwide standard for structured data. There's no requirement, I think, for research data that is sort of individual researchers to meet these kind of high standards, but the principles are very good and they can be applied to basically any data in all of science, in my opinion, but especially throughout climate science. I'm going to talk just about the ACS first. So the Australian Climate Service in Project 3, so ACS is a very large project that is, it includes Geoscience Australia and the Bureau of Statistics and some emergency management kind of departments in the federal government. So it's a very, very large structure. It's a bit difficult to comprehend for myself. We're working in Project 3. I'm pretty sure it's Project 3. It used to be called Project 2. I think I still need some clarity around what project number it is. Shunsu's nodding his head. So in Project 3, we'll be doing high resolution reanalysis, which is Barra 2, which Shunsu talked about yesterday. We'll be doing looking at sub-seasonal to seasonal outlooks of hazards, so ACCESS-S and ACCESS-S2, multi-year to decadal outlooks with ACCESS-D, and the regional climate model downscaling of CMIP6 predictions with BARPA and CCAM, and then connecting into other regional downscaling efforts as well. I'm going to mostly be talking about the downscaling efforts here because that's really where we've focused a lot of the sort of data work at this point, and sort of developing some frameworks and workflows for that. So I'm going to talk about our workflows for these data products for the downscaling. Starting with a regional climate model simulation, which is just the raw outputs, which we call level 0 data. We'll be creating our Cortex compliant output data. So this is the DRS data. This is model output. This will look very similar to what's in CMIT 6 and what was in the first round of Cortex. So this is our really standard model output, really just what comes out of the model, formatted in this DRS structure. We'll also be doing some bias adjustment using tools like QME and MRMBC, which will also be structured in the DRS. That DRS is called Cortex Adjust, which is an existing defined DRS that we'll be applying to this data. We've also got 2 additional products that we're going to be creating, and we're going to be hopefully formatting and structuring these into a DRS, which I think is a bit novel. First off, we're going to be doing some verification. So we're going to define some standardized verification that we're going to be doing across these models. We're talking bias maps, realized added value calculations, really comparing the model output to reference data sets, whether that's the parent GCM, the host GCM, or observational data sets like AGCD. That sort of verification, model skill kind of analysis that we want to do. So we're going to try and define that in terms of the data that we're saving, so that we can develop a tool that we can run on the model output to create a standard set of verification metrics that we can use to sort of demonstrate then the validity of the models. Additionally, because it's ACS and it's hazard focused, we're going to have a separate product as well in the DRS called indices. The names of all of these 2 boxes here on the right are still a little in flux. We're still working on details. We're going to save all of this kind of stuff also in a DRS that's going to be have the same kind of metadata structures. So we're talking fire hazard and all the different sort of hazards. ACS has looking at different hazards from fire, heat, cyclones, coastal floods, I believe. We'll also be doing extremes analyses, that kind of stuff. So we'll be looking at the ClimDex list of indices, tempest extremes, generalized extreme values analysis. So we're going to really structure the kind of derived metrics and derived indices that we want to take out of the data that will feed then into hazard analyses and those sort of flow down products, ultimately leading to plots, reports. This plots and reports sort of this is really very small box, but it really represents everything that's going to customers, going out into both reports and papers, deliverables into EMA, the emergency management, all that kind of stuff. The benefit of saving not only the model output, but the derived indices and the verification metrics really means that we can access everything in an interoperable way. Everything's then fair data. We can save everything into an ESN catalog, and it can just be explored and analyzed and accessed both by researchers and by customers in a much easier way. So everything that's in this red circle is going to be in the DRS. This DRS, I've got a similar schematic that I'm just going to walk through because I want to really demonstrate what that's going to look like in a practical sense. My example here is to say a BARPA simulation of ACCESS-ESM, which is already being run, I believe, at the moment. So we'll have in this DRS, which is a Cortex-like DRS, we've got all the details of all documenting all the simulation, both their host GCM and the RCM that's being run, so BOM, BARPA, R, and down to saving the model output. So we're talking down here on the left-hand side in the orange, we've got the model output, we've got monthly, daily, hourly data, that kind of standard. We'll also have alongside that the bias adjusted output. we haven't decided exactly what bias adjustment methods we'll be using, but as I said, the framework already exists for that. Additionally, we'll be trying to define a whole separate branch called verification, where we'll be saving bias maps, root mean squared error kind of calculations, realized added value, those kind of metrics in a single sort of whole chain of products. And then a separate one called indices, as I mentioned before, where in here, these are frequencies. But when we're talking about verification and indices, frequencies kind of don't really capture all the details. And so these are more going to be categories of metrics. So we're talking the ClimDex list, extremes analyses, fire metrics, and then we'll have more according to whatever we kind of need to generate. This framework allows for a lot of flexibility, allows for us to evolve it over time, grow it, add more products, then ultimately feed that into the intake ESM catalogs so that we can then really build on it. This is really just an idea that we're going to hopefully then build it into our workflows. Additionally, we'll also be calculating these kind of indices for the host GCMs as well. So as here, I've just got a little example of calculating these same indices for the ACCESS ESM model output as well, so that we can compare them directly in the same DRS. I also just want to mention real quick the National Partnership for Climate Projections. So it's called the NPCP. So it's a coalition of partners from all the different states and territories, the Federal Department of DOR, NCI, universities, BOM and CSIRO, all kind of working together in a collaborative effort to coordinate regional downscaling of CMIP6 particular. So it's managed by DOR, and it's really just a sort of coordination effort. So there'll be efforts. So there's three working groups in the NPCP: the science and modeling, which is more of the general kind of science direction; data and code group, which is data infrastructure, software requirements, those kind of things, which I sit in, and Ben Evans is the chair. And then the third working group is services, which is more of that sort of customer-facing working group. We're hoping that we can provide a forum to discuss, among many other things, what kind of access runs that we might want to use for projections. We're obviously using CMIP6 runs now, but so scoping out for additional larger ensembles, these stabilization runs that Matt Chamberlain kind of mentioned yesterday might be very useful for climate projections. Scoping out to CMIP7 and what kind of models that ACCESS will be running, and generally the future of ACCESS and CMIP along machine learning, digital earths, and that kind of really broad, long horizon kind of discussions as well. That's it for me.
We are running a bit out of time, but we can probably do one question when I change Thomas.
Hello. Hello, Thomas Loughran from CSIRO. So the ACCESS input is nowhere near as organized as the CMRIzed output. And I think from what I can tell, forcing and restart files for ACCESS is spread out over multiple projects, and it's very frustrating to find where everything is. Do you have a plan on what to do about that? As a suggestion, when I was at MPI, the MPI ESM, they put everything in a pool directory in the root folder of their HPC file system with subfolders for each model. But that was good because I knew where everything was, but the downside was that people just dumped things there and didn't document it. So
yeah, a DRS, having everything in a DRS, it almost forces you to document things. It forces you to document the data, which is the real benefit, I think, of a DRS, because then everything is very structured. You have, a DRS requires a controlled vocabulary, which requires you to define the vocabulary, which requires you to document the vocabulary. And therefore, even at the very minimum, if that's all you've done, you've really just got a list of terms. We've got then a lot more documentation than a lot of the data that exists currently. Is your question more around the input data into ACCESS, the forcing data and things like that? I think that the concept of structured data and a DRS can be applied to any data set. at all. So we're talking input data, output data, forcing data, reference data, observational data, anything. So yes, basically my short answer is yes, we should define a DRS.